record on this computer. Perfect, it's been recorded.
Fantastic.
And let's share the presentation now. Share screen. Where's the presentation? Let's see if it is. Okay, and it's going to be lecture 9. And we're going to reduce this. And let's go on. So this is very welcome to the 9th lecture of Physics 140 this semester. I would like to start by reviewing a bit of what I did last time in terms of special relativity. And the idea is the following. Then we discussed the two postulates. You know, all the physical laws are the same in two. That seems very sort of trivial and correct in a way that the physical laws are the same in inertial reference systems, and that is, you know, something we knew from Galileo a bit. And the second postulate that is very important is that light travels at the speed of light, no matter how the observer or the sources are moving. Okay, and so we actually discovered that has a lot of implications in terms of how to transform velocities, how to look at events in one system and another. And the first one is the measurement of time intervals between two systems. Okay, so the idea is the following: if you have a watch and you're looking at your watch, let's say we go to the train station, and you know, we somehow synchronize our watches, and I put something on my watch and you put something on your watch, and let's say we can actually record the year also, so because that could be a problem also. And they are very well synchronized. You get on the train and you are traveling at the, you know, half the speed of light in this fantastic train that we have just built. Your clock in the train will actually work slower than mine, essentially. So if you're in the train and you travel through a year being in the train, let's say for the sake of argument, and you come back, and depending how close to the speed of light you were traveling, you will be much younger than me. Okay, and there's a paradox in here, because if we cannot make a differentiation between two inertial frames, why am I not the older guy, the younger guy, and you're the older? You know, there are arguments there to actually tip the balance in one side to the other. But the thing is, in this, you know, minimal experiment that we have here, we are measuring a time interval, and the time interval measured inside the train is actually shorter than the time difference measured outside for the same events. So what are the events? I have, and this is chosen very carefully to be a ray of light, because there's no ambiguity about what the speed of light is. The speed of light is c, no matter what. Oops, what did I do? Oh, okay, I did nothing wrong. It is simply this system that is telling me that it has stopped recording. No, not stopped recording, that it has actually, I don't see my presentation now. let me stop share for a moment. And let me share again, because there's something funny about this. Okay, here we go. So what we did last time, I assume I did this part. Is that right?
Yes, if I remember last class, we did this same experiment.
Yeah,
or at least
this experiment where this woman is actually looking at a ray going up and down.
Oh, no, actually, no, I don't think we did the one with the ray going up and down. I do remember us doing the one of the lightning striking at the same time at two areas of the train, where she saw one lightning strike earlier than the other.
So said we arrive only to simultaneity. We didn't deal with this. Oh, that's bad. Okay.
That's what I recall. And
well, you know,
wrong. I'm not known for having the best memory.
That I actually uploaded, I did the whole thing. I did this, even though I didn't do it on the real class. But you know what? You know, let's do it again. So
fantastic.
Let's do it again. Let's get into
I do remember that we had like less time last class. Have I think it's the class or at least the presentation would have been longer, but the time constraint we had of an hour and 10 minutes was a little bit too short.
Okay, let me get into what do I want to do more. I want to let me open it first. Yeah, let me open the presentation. This is not it. This is not it either. Let me go back here to lecture 8. Lecture 8. Let me go to PDF. Lecture 8. Now, where's this? Oh, here, let me share. I assume this is lecture 8. It's not clear. Yes, it is. Okay. So let me get to the point where we went to simultaneity. Is this part of it? And then we had to get to this experiment, okay? Which is the same view graph, but you know, I think I cut a few things back, so let me put it completely here. So we have a different experiment now. We have this, you know, then again, this guy is called Stanley because it's standing in the station, and this woman is called Mavis because it's moving. Mavis moving. I guess that's the type of observers that we have. And this woman over here has this type of a clock. It has a source that sends a ray of light to the mirror, and it comes back to this point O prime. Okay, so for Mavis, the time. I changed the name. No, it's Mavis. It doesn't have a U there, actually. For Mavis, the time interval for the light to go back and forth, it goes from here to there and back, is simply delta T naught, which is 2D divided by C. D is the distance between this guy and this guy, okay? Now, this train is actually moving, and this fellow over here, Mr. Stanley, is looking at the same set of events, looking at the ray of light starting out from O equals to O prime, going up and coming down, okay? What does he see? He sees something different, because he sees that the light will cover an interval of time, delta T, will be the time it takes the light to go from O to the point on the top and come down. Since this thing is actually, the train is moving at a constant velocity, it happens that this L and this L are the same, meaning that this transversal distance here. This distance here, it's not altered by as seen by Stanley or seen by this woman inside maybe it's inside the train. Okay, so delta T will be equal to 2L divided by C. So it's 2 divided by C by L. How do I calculate L? It's simply this Pythagorean triangle here is UT divided by 2 square plus D square plus this distance over here. Let me try to use the pen because you're not, this is much better. Spotlight. Okay, spotlight. Here we go. So is this distance and that distance? Or I can even use the other one, the new one, the vanishing pen. Would it make it perfect? This distance and that distance. Okay, so both distances are go into the calculation here. So what I can do next, let me see if I can view as, no, that's not zoom, it's this thing. Why doesn't it go to full screen? I don't know why it doesn't do that. I have to go out. Well, forget it. Let's do it as it is. It's not a big deal. Okay, so we have this okay. Now it's not doing anything. Okay, what if I do this? And now go here. No, this. I go to zoom. And now I share more. Share screen. Share. Okay, let me see. That's okay. That's better. And I have to get the pen. I think they are making improvements in the program, and they don't tell us actually. Okay. So this is the time interval measured by Mavis, and this is the time interval measured by Stanley. And I want to, and the only thing that ingredient that this thing has is that the speed of light is the speed of light. Okay, because that is what Einstein proposed us as a solution for all these problems. Okay. And so delta T squared, then you can actually, from this expression, you raise everything squared, 4 over C squared plus everything here. And you have to, you know, find out what is the value of delta T squared. So place everything in there, and delta T squared is simply 4 D squared over C squared divided by this, no, it's 2D divided by C, which is delta T naught is equal to delta T, but divided by this factor. This factor over here, this factor is 1 minus U squared over C squared, right? So what are we seeing here? This is the interval seen by for the same event. This is the interval for this event seen by Stanley, And this is the interval seen by Mavis. Okay. This is an event that happens in the same location. There's a difference in time between an event that happens in the same location in space. The ray of light gets out of O prime, the ray of light gets back to O prime. So everything in Mavis frame occurs at O prime. So here, between these two events, this is something relevant, okay? And delta t is the difference in time for this, as seen by Stanley. And look, I have done this thing. I have graphed here the two things. Here I have delta t. Here I have beta. Beta is equal to the ratio of u over c. And when this thing is 1, the time interval seen by Stanley can actually go to infinity if the train is traveling at the speed of light. Okay. So this is a good reason why we cannot get to the speed of light, because the time will go very fast for a few people, and that's exactly what happens. So this is the expectation in the red light of what will happen under Galileo. Okay, it doesn't recognize the speed of light as a certain limit or a special number. So delta t and delta t naught will be the same. Okay, so this delta t will be always the same, no matter what. But here we could see that it fires up, and we have to do this. This is what is required in order for the postulate to be true. What is the postulate? That light travels at the speed of light no matter what the velocity of the source or the observer is. Okay. This factor over here, 1 over the square root of 1 minus v squared over c squared, is called gamma. And the reduced number, this guy here, is called beta. So I could actually write gamma 1 over 1 minus beta squared square root. Okay. So, but this is a real important aspect. And this number here, where there's a significant difference between this, well, it doesn't have to be very significant. If there's 1% difference between delta t naught and delta t, this difference, the number here is about 14% of the speed of light. When the number is 14% of the speed of light, the increment in time is about 1%. Okay, so you really have to be going really fast to actually see this line, the blue line here, take off with respect to the red line, which is what we are so used to believe it's true, until somebody that was much smarter than us told us, no, come on, guys, that is not really what's going on. This is what is going on. Okay. This in particular is what we call a proper time transformation, meaning the term proper time describes the time interval between two events that occur at the same point in space. Okay, what was the point in space? O prime. And there is no preference between this inertial system and this inertial system. The thing is not you can reverse things. You can say, we can describe anything like Mavis is standing up and this guy is moving back at the speed of light, or at a fraction of the speed of light, which is u. No physical object can travel at the speed of light, and because you will need an infinite amount of force to get there, and we will see that. Okay. So this is the term proper time describes this type of interval then. Okay, so this is something very singular. This is something very unusual that we are not really familiar with. Okay, you have to be very careful in when to apply this expression. The only time that you can apply this expression is when both events that are measured here as delta T naught occur in the same point of space, okay? That's when you can do that. Okay, that's half the story. Look at the second part of the story. Measurement of a length in the direction of motion. So here is Mavis, again, sitting on the train. And so she has set up this nice experiment here and says, look, I'm gonna measure, I wanna measure this length here, L naught, which is not moving with respect to Mavis. It's on top of the seats here. And so she is gonna send, and she's gonna measure it using the speed of light, which we know it's a fixed value. So she will send a pulse of light, bounce it from a mirror, and come back to the source. And she's gonna measure the difference between those two events, and will say, look, 2L naught divided by the velocity of light is equal to the difference in time that I measured. So if I know the difference in time, I know the length here, okay? So that is the, and the ruler, as it says here, is stationary in Mavis frame. And nothing, it's 2L naught that the thing travels. And now what I'm gonna try to see is how does Stanley sees the same experiment, okay? He looks at the thing and see the light coming out from here, start traveling in space, but for him, the ruler is not stationary, it's actually moving. So this guy is gonna arrive at a later position. What later position? Well, it would be L plus UT1. Notice here that I've, or even the book conspicuously has dropped the L naught here, because the length L that Stanley is measuring an object that is moving. And it's not the fact that you know, you have to look one side or the other simultaneously, which is really a problem actually in here. But the thing is, this length is actually a length that is in a different reference frame, maybe it's reference frame. And it could be that whatever he sees of this is different. And as we should find out, is different, okay? But at the time being, this is what he sees. And then the lights start to travel back in the different direction, okay? So this is the situation. Delta T naught is the difference in time seen by Mavis, is 2L naught divided by C. Oh? And this is a proper time because it went back and forth, okay? So two events happen in the same point in space in Mavis reference frame, okay? So how is the same event seen by Stanley? This is what happens, you know, if emit the light, this will be, I call this L1 to make it different from L naught definitely. And if they are different, this will come out, okay, in the calculation that we're doing. So this is the time it takes the light to get to the mirror, and then when it gets to the mirror, it has to go back. But at the time, you know, it has to go back. The train is actually moving. So if the train is moving, and you know, sort of meeting actually the ray that is coming along, so he sees that if u is the velocity of the train will be displaced by u t2 minus t1. T1 was the time when remember these are time travels in only one direction. I don't have intervals here. I have the absolute time from the origin, and the origin was measured when the two reference frames were together. And the two reference frames were together here. It gets to T1, and then from from the instant it actually bounced from here, time travels back, and when the clock says T2, the ray arrives at the source again. So what is the actual distance that the thing had to travel? Well, you know, since the train car was displacing, it was moving by u times T2 minus T1 by the interval of time. So the light was traveling that direction, and the source was traveling in this direction. So this is the actual distance that the light actually covered. Okay, so let's write the equations here. So c times T1 is the time it times the velocity of light it takes to travel this distance, and that distance will be L1 plus V plus U times T1, which is the displacement of the train. Okay, this is the time T1 taken by this for this event to happen from here to here. And now this distance over here is the light has to travel c times T2 minus T1 to cover this distance, and the distance it's actually covering is L1, which is this distance here, minus the displacement that the car actually made going in that direction, which is u times T2 minus T1. Okay. So what I'm saying here, take this equation, write it up here. Is the same equation? Yes. Well, what I have done here, I've okay, from this equation, what I want to do is actually eliminate from these two equations, eliminate T1 and leave only T2. So how do I do that? I just there's something wrong here, actually. I have the impression there's something wrong. I'm going to check it later. But this relation here, what is what I don't like here? This should be equal to this, and this is u times T2 minus T1. Let me see, u times T2 minus T1. So yeah, there's something wrong here. Okay, this expression has something wrong, but this is correct. Okay, so this is why I need a pen to actually write in this thing and correct there's something wrong here that I don't. At first sight, I don't see the connection. What I have to do is take this equation and replace T1 here. Okay, T1. I want to write T1 as a function of U, L1, and C, because I can, you know, take T1 out here and write it. And when I do that, this should be T2 actually. So I should leave an expression here that's only a function of T2. If I do that, I can take out T2 and express it only in terms of length and velocities, which is what I want to do here. I reorder terms, I write it like this, and I get this expression. T2 is equal to L1 times this. Okay. Simply adding these two things up, and look what happens. You get T2 is equal to this expression completely, where you have 2L1 over C times this factor here. But now I would like you to remind you that T2, and this is the time between the light going from here to there and coming back. So in terms of whatever Mavis is seeing, even though that doesn't happen in the same reference frame or in the same position for the reference frame seen by Stanley, which is standing on the station, because this point is actually moving, in terms of Mavis, is something that happens in the same position of space. So it's an interval of time between two events that happens in the same position in space. So this is a proper time. So what is the proper time? Well, in the time it takes for those two events to occur in Mavis reference frame is simply delta T naught, which is L naught divided by 2L naught divided by C. Okay, so this is what I'm saying here. So T2 is a proper time. So if it is a proper time, I'm sorry, delta T naught is a proper time. So the time seen by Stanley of this proper time is exactly T2, which is exactly the time it takes the thing from coming out from here, do the whole trip and come back. So this is the expanded time seen by Stanley, which is delta T naught divided by 1 over U squared over C squared. Okay, so delta T naught is 2L0 divided by C. So I write the whole thing like that. And if this is equal to T2, I can replace it here in this expression. If this is T2, I can replace it in the expression, make the two things equal, and now I can find a relationship between L1 and L0. Okay, so what do we find? We find that the length at rest, which is L0, the thing that actually Mavis is measuring, this is the length at rest, has to be multiplied by a factor that is less than 1. Remember, this factor here now, it's not 1 over this, is the square root of 1 minus U squared. This is 1 over gamma. So 1 over gamma is a number that is less than 1. And this number less than 1 has to multiply this length. So actually, Stanley see a contracted length. Okay, so if I graph these two things, just as I did before, L naught is the actual rest length at rest, which in the case of Galilean transformation, the length at rest and the length of the moving objects are the same. Okay, I don't know why did Einstein got the idea that they were different, you know, because it's such a familiar thing that it should be the same, but they are not. They are not. The length that I see of an object by moving by him is actually short. How much shorter? This is the relationship that holds. So we have two phenomena that are really at the core of special relativity. One of them is the dilation of time. So time moves. The clocks move slower in a moving object, and actually the contraction of length. If I'm measuring a length of an object that is moving, the length is actually shorter. Okay, this is it. And so this is the implication of relativity, as odd as it could sound, you know. But it has to do with solving the problem of the speed of light. What are we getting into here? We're getting into something that relates. I'm sorry, something that relates to the transformations of coordinate between one system and the other that is non-trivial, that is completely different to what Galileo was proposing us. If I do this thing under Galilean transformation, none of this would be valid. As you could see, the difference is certainly very evidently distinct. Okay, when is distinct? When the velocity is very close to the speed of light, when beta is very close to 1. Okay. Let me see. Okay, I guess this was the last transparency of the last lecture. So I'm gonna take over from here on the next. So I'm gonna I imagine I have to stop share. Yes, I do that. And I'm gonna open lecture number 9, which is, no. Lecture number 9, which is here. And open the is this one? Yes. Okay, we have done everything here. Length in the direction of motion. Okay, so am I sharing this with you? No. Okay, here is. Okay, this is the right lecture. So we are ready now to actually undertake the task of finding out view full screen. Okay. To find the alternative to the Lorentz, to the Galilean transformation that is equivalent to the Galilean transformation between two separate moving systems. So to set the frame is the following. We have a reference systems as shown here. Which is the following. We have a reference frame which is S. Okay, this one here that has an origin at O, and then this reference system is moving with respect to this one with U, and this is the prime system. In the prime system, everything is different. We have T prime, X prime, Y prime, zeta prime, and here we have X, Y, and Z. So we know that the dimensions in the direction perpendicular to the motion are conserved in both systems. There's no relative motion in this direction, so Y and Y prime should be the same, C prime and C should be the same. But then again, we have just seen that the time interval measured in this system is different from the time difference measured in this system. So T prime is different from T, and X prime is different from X. Okay, so X prime is different from X minus UT. This would be X minus UT would be Galilean transformation. Okay, so let's see how we can argue what the actual transformations are. Okay, so let's first take the X coordinate is linked to X prime by knowing that X prime is a rest frame length. Yes, this is measured at rest between 0 and X prime in the system O prime. So the distance measured from the ground here, from 0 to X prime, is simply ut plus the actual length that I could see here. But since this is a measure at rest and this guy is actually moving with u, it means that x will be equal to ut, which is this distance, plus x prime multiplied by 1 minus u over c squared, because there's length contraction. So the length in this direction is actually constructed. There's a construction. It's constricted. That's it. Simply because I'm seeing the same lengths, ox prime from I'm standing still, and this is the dimension in the moving frame. Okay, so this is what we have just seen. So essentially, if I use this relationship, I can find that x prime is equal to x prime. I just, write x prime is equal to x minus ut over this term. So this is half of it. So we can write x prime is equal to gamma x minus ut. If you remember, for a Galilean transformation, the only thing that I have to do is make gamma equals to 1, and this thing and this transformation is equal to the Galilean transformation. Wow, this is great, because this is exactly what we want to do. What does it mean, gamma equals 1? Gamma equals 1 means that this term here is 0, or the velocity is very small compared to the velocity of light. Perfect, because, Galileo makes a lot of sense in small velocities, and it's only at high velocities that we need the Lorentz transformation that we are trying to deduct here, okay? So this relationship should be symmetrical to saying that O is the system that moves away. Let's say now I have this guy standing up, not going anywhere, and this guy is moving back. Okay, so how does, if that is the situation, the only thing that I have to do in this equation here is replace where it says x, when it says x prime, I should write x, and when it says x, I should write x prime, and I should change the sign of the velocity. Because if I do that, this transformation will be symmetric. And as Einstein told us, there should be no difference. There's no preferred reference frame here. So they are both equivalent because they are both inertial frames. Okay, so this is what I have done here. And I get to relation 2 that says that x, okay, I drop the prime. Now in this guy, I add the prime. And then, well, u squared, it doesn't really matter. U squared is u squared. It doesn't matter if I change the sign of u. I change the sign of u to minus u, and that I change this sign of this. Let me write this thing again. Okay, so what did I do? Here I add a prime. And here I add a plus sign, and I get this equation, okay? And now I know equation 1 and equation 2 are both valid because they're sort of deducted following the same contraction of length, essentially. But I'm going to use them to eliminate x prime from 1 and 2, meaning, x prime is not what I really want to. I just want to keep the time. T prime. Okay. Why do I want T prime? Because x prime depends on x and t, and I want to write T prime dependent of t and x. That's exactly what I'm going to happen if I actually get rid of x prime between equations 1 and 2. I do that, and this is what I obtain. Equation number 3. You can follow this, bit of algebra here. And this is what I obtain. that Ct prime is equal to gamma times Ct minus x times u over c. Okay, if you look at this expression, you can see the similarity with this expression. You have a gamma in the front. Now I multiplied it by c here just to make it a length. So instead of a time, I make it a length. If I make it a length, it's easier to compare to this. So here we have x prime, and here we have x. Here we have Ct prime, and here we have Ct. And then we have x in this position here, in this expression, instead of time. But it has to be properly scaled by u. There's a u, but since there's a u, the units won't match, so I have to divide by c in order for this to have the right dimensions. Perfect. So the space coordinate transformation is analogous to the time coordinate transformation. So this is the great thing about relativity. You know, time and space are somehow equivalent in this. More so in general relativity, which is a second step of this theory. But you know, for the time being, this is good enough. So this is the Lorentz transformation. This expression here. So x prime is equal to gamma x minus ut. Okay, so this is coordinates x. This is the coordinate x prime. This is origin O prime. This is going away with u. Okay, if that is the case, this is a transformation from going to x prime to x. Y prime and C prime that are perpendicular to the motion are not transformed at all. And T prime is also transformed, and it's transformed this way. This is probably the most difficult thing to actually understand, you know. Why is this thing true? Okay. Well, this thing is true because otherwise, you know, it won't be true that light travels at the speed of light independent of the motion of the objects, okay, of the source and of the observer, okay. Okay, let me see if I go, oops. No, I have to get out of the pen. Yes, okay. Yeah, these are the inverse transformations, what I have here. The only thing that you have to do for the inverse transformation is replace x by x prime and change the sign of the velocity as we have already discussed. So if this set of equations are the Lorentz transformation, these are the corresponding inverse Lorentz transformation for the system. Okay. Let's see. Let's re-examine the implications of this coordinate transformations. In this system, the coordinate of x, y, z, and t, or since y and z, you know, are the same in both, we are not going to consider them very much so. We are very much interested in the ones that change, which is when looking from one system or the other, and these are x and t, okay? A set of x and t coordinates correspond to an event. What does an event mean? It's something that happens in a certain position in space at a certain time, okay? So this is an event. So let's examine the thing with the light rays that goes back and forth in Maybe's train car running at you by the station. So what are the events? E1 prime is the event that happens in the prime system. Light leaves the source at x1 prime equals to 0 and t1 prime equal to 0. At E2 prime will be the time that the light arrives at the mirror. Light arrives at the mirror at x2 prime, which is equal to L naught, and T2 prime will be L naught divided by C, which is the time measured by Mavis that the ray of light took to arrive there. E3 prime will be the light arrives back at the source. That will be x3 prime equals 0, because the prime reference system, the source, is actually at the origin, and it's not moved because it's in the train, stationary with respect to Mavis. And the time is simply 2L naught divided by C, as measured by some stationary observer in the train. Okay, so I make a list now of the events. This is the event. These are the prime. I should drop the 1 here. These are the E primes, and these are the E's. The E prime occur at this coordinate, and they also occur at this coordinate in x equal to 0. And what does it mean is that if this is 0 and this is 0, x is 0. Perfect. So this, if I know this, I know exactly what these values are. Okay. So when once want to solve a problem, you just define the origin of a problem, solve it in a reference system which is easy to solve, and then go back and make the transference using the Lorentz transformation as something seen from a different observer. Okay, this is sort of the technique for solving any problems in special relativity. X2 prime occurs at L naught, where? Here at the front of the mirror. The T2 prime is the time it arrives there is L naught divided by C. Okay, perfect. So what are the coordinates? How are the coordinates transformed then? Well, the thing is simply just replace these values of x prime and t prime in no, here. Replace here, I'm sorry, x prime and t prime, and you will find how much x value is and what the value of t is, because we know t prime and x prime, so we can find both. So the question is, we have to find the two values, okay? What is x2 and what is t2? Here is the expression for x2, and here is the expression for t2. And if, this doesn't look very nice here, but, all the numbers are in there. So when you sort everything out, you get this funny expression with the square root of 1 plus u over c divided by the square root of 1 minus u over c. And the difference between the coordinate and the time is a factor of c between both. Okay. The question is, you really have to get the right length for that to happen. Okay, which is the length that is actually traveled by the light as seen by a stationary observer here when it goes from here to there. Let's go for T3. For the third event. The third event is the one that happens at x3 prime equal to 0, when the light is back at the source. The time it has taken for that to do is 2L0 divided by C, because the observer is stationary with respect to the light. And what about X3 and T3? Here they are, X3, where does it happen? Well, it's look what comes out of this. According to, since x3, this thing here is 0, the position where that actually happens is gamma times u times t primes times simply gamma u t prime, gamma u t3 prime. That's it. And we know t3 prime, so we can replace it here. So it's gamma u 2L naught divided by C. Okay, so this is the coordinate at which the source will be when this has gone back and forth. Okay, how can we think as seen by Stanley, which is this T3 here, okay? Look at this. 2L0 divided by C is simply what? Is simply the proper time for the whole event, okay? If I multiply that by gamma, what does it give? It gives me the time seen by Stanley in the standing reference frame, okay? Which is the same logic as before. So you can recognize in this expression over here that gamma times 2L0 divided by C is the time, is the proper time as seen by Stanley. Times U is the time the train has taken, been displaced during the two events, which makes complete sense. And you even don't have to think about it because the Lorentz transformation give it to you, okay? Okay. I think we still have 10 minutes to go, okay? So
it should be around 10 minutes.
Yeah, thank you. So the next step is how to transform velocities, and this is a bit odd because now it's very evident that things are really different from relativity as seen by Einstein to relativity seen by Galileo. Okay, so the transformation of coordinates between the two systems is x prime. This is, you know, is x prime will be the position of a system measured in the moving system, yeah? And x would be the position as measured by the standing system, this guy over here, okay? So we have this relationship for x prime and for t prime, and we want to find out what the velocity is. And if I differentiate this thing, dx prime will be, everything will be dx here, and I've done this. This is dx prime, is gamma, which is a constant, multiplied by dx minus u times a differential of time, okay? And I do the same with dt prime, the same expression. This is just a mathematical statement here. But then I said, look, vx prime is dx prime and dt prime, and dx is dx and dt. So I go and make the quotient of these two things, the dx and the dx prime and dt prime, and get this will be the velocity vx as measured by the moving reference frame, and you know, this is the expression. It doesn't tell you much, but unless you divide this thing by dx, by dt, I'm sorry, divide on top by dt and divide the bottom by dt, and you get this very nice expression here at the bottom, which is vx prime is equal to vx minus u divided by 1 minus u vx divided by c squared. What would Galilean transformation show up? Galilean transformation would show only the top part, and this part would be missing, okay? What does it mean? Well, that the product of these two things is very small compared to c squared. That's why Galileo is good for small velocities, okay? But for real fast object, this is the way to transform velocities, okay? And I encourage you to take a look at the book on this, okay? So this is the velocity v prime measured in this system. It's expressed like that. And this is the velocity v as measured by this standing system. And this is moving with u. This is the velocity of an object in O prime, okay? The u is the velocity of displacement between the two systems. So v prime will be vx minus u times 1 minus u vx over c squared, and the other two directions perpendicular to the motion will be the same. Okay. So this is the example. This is the example we have. We have something that is moving. Let me. Yeah, this is the example that we are going to consider. We in the lab frame, which is O, we have a particle going, particle 1, which is going with in the positive x direction with velocity c over 2, and we have a second particle approaching this one with a velocity c over 2. In a Galilean framework, what would be the relative velocity between the two particles? You should have no doubt on this one, huh? Yeah. Okay. Well, you know, if I'm standing in this guy, what would be the velocity of this guy coming back? Okay, because this, but remember, this is measured with respect to this frame. Okay, so essentially, what I'm seeing here, if two things are heading a head-on collision with half the velocity, they should be approaching each other with the velocity of light, essentially. They should be approaching them with c. But we have seen that this is not the case. It shouldn't happen, you know, in relativity. Yeah?
All right.
So we should use this expression here. So the two objects approach each other in the laboratory frame with c over 2. What is the relative velocity? Answer, we will use a moving frame in particle 1. So we will put this is particle 1, and in particle 1, the velocity of the frame is c over 2, and we want to see this velocity, which is minus c over 2, in the fixed reference frame. We would like to see how does it look in the x prime reference frames, in the O prime reference frame. So V2 is minus c over 2x. Okay. What is V2 prime? Well, V2 prime is this. So I replace Vx. Vx is minus c over 2. Perfect. Then it says minus u. What is u? Well, u is c over 2, but for this particle. Okay, so it's c over 2. Maybe I should have chosen a different value of velocity to make it different here. Huh? Next time. And then this is divided by 1 minus u is c over 2, and Vx is minus c over 2. Okay, so here I have minus times minus is plus, the c squared cancels the other one, so I have here 1 minus 1/4. I'm sorry, 1 plus 1/4. And at the top I see c. So V2 prime is equal to that. So the velocity of the approaching particle will be minus 4/5 cx. This is interesting because even though Galilean here would say the velocity of approach is c, here we have an evident reduction of the this apparent velocity, and this is something. This is real. This is something we have to really take into consideration when seeing objects displaced on the different reference frame systems. Okay, this is very important, and you know, I will leave you with the. Oh no, this is not. Yeah, okay. We will take this thing next lecture. Okay. We are bombarded by muons. Okay, yeah, this is an example of, yeah, I will load it up, okay, and we'll take up these two subjects in the next lecture. So This
All
will be
right.
the end of things for today, unless you have any questions.
No, not really, to be honest. Thank you for the lecture.
Okay, thank you for coming. You know, you I'm talking to a human being. You know, so this is good. And so we will be meeting. I guess I put a homework here at the end. So let's not do that. Let me see. Did I do that? No, I didn't. No,
No,
I
it doesn't
didn't.
appear to have a homework.
No, it doesn't have a homework. No, it doesn't have a. It was the other lecture that had a homework. This one doesn't have a homework. Perfect.
That means there's a homework for this Thursday from the previous lecture, if I'm not wrong.
Perfect. Perfect. That would be it. You know, no homework this lecture. I'm gonna write something up for the next one for Thursday. Okay.
All right. Thank you very much.
Okay. Thank
I
you.
hope you
Thank
have a very
you.
good day.
Okay. Same to you. Bye bye.